Welcome to the ChemDoctor, and this is the second video on reaction mechanisms and determining the validity of elementary steps. Now, in the first video, what I did was I laid the groundwork to understand how we basically analyze the slow versus the fast step. And remember, the key thing here in the reaction mechanisms videos is that it's important for the viewer to understand that we're dealing with an overall balanced equation. That would be the equation that I'm showing up on the right-hand part of my screen here, which has already been characterized by the chemist experimentally, and an experimental rate law already determined for this reaction. So in a reaction mechanism, what the chemist is doing is trying to understand the actual pathway that would explain this rate law. All right, and in order to do that, what they do is they come up with a series of what they call elementary steps, which I'm showing over here in blue. The elementary steps combined represent a possible reaction mechanism that would explain this experimental rate law. Now, when I say that this is a possible reaction mechanism, this series of elementary steps literally is a hypothesis. And what I want to do in this video is to show the viewer how we would validate this series of steps to either invalidate the hypothesis or to validate this as being a possible explanation for this rate law. One of the key factors in this is knowing which of the steps in a series of elementary steps is rate limiting. And in the first video in this area, I explained how you analyze that. To summarize very quickly, if I was to write an energy diagram for this reaction or reaction coordinate, for example, the elementary steps here occur in two steps, and the first step is the slow step. So you would expect it's the initial peak here to be higher for that step than for the subsequent second step of the reaction, or second step of the reaction mechanism. This platform here would be the reactants, and this platform here would be the products. All right, and if I draw a line straight across like this, we draw an arrow up to this first peak. The E sub A here, the energy of activation for the first step, is much greater than the energy of activation for the second step. All right, so E sub A1 is much greater than E sub A2. Now, what does this mean? It means that the first elementary step here is the rate limiting step. So basically, the rate law for these elementary steps has to be defined based on this step. Now, how do we validate whether or not these two elementary steps are a possible explanation for this experimental rate law? All right, the first thing that we have to do is we have to show that you can sum these two equations together and actually get back the balanced chemical equation. So let's go ahead and get that part of this out of the way, and then we'll come back to how we deal with the rate limiting step here in terms of the elementary step. All right, so when we compare these two equations, you can see that the NO3s cancel. All right, and one of the NO2s cancels, and when we sum this together, then we're going to get NO2 plus CO going to NO plus CO2. So this series of elementary steps actually passes the first part of the validation process, because this equation that we got from summing the two elementary steps is in fact equal to the overall equation from the overall balanced equation for the reaction. Now let's move on to the next part of this, and the next part of this has to do with evaluating whether or not we can actually get a rate law from an elementary step of this series of steps that matches the rate law that was determined experimentally. And this is an absolute requirement. If we can't do that, then we would invalidate this. And then I might be moving a little bit faster, so let me just back up 1 second and say that if we had not been able to sum these reactions together or these equations together and gotten the overall balanced equations, then we would have been done right out of the gate with this. We would not be going on to this next step. So to deal with this next step, what I want to do first is to rewrite the elementary steps so that we don't have clutter here. So the first elementary step is this one. To produce the NO3 plus the NO. All right, and then my second step is the carbon monoxide plus the NO3 going to NO2 plus CO2. And again, the very first elementary step here is the slow step. This is my rate determining. I'm going to go ahead and write that in now. All right, and the rate determining elementary step is the step that we have to be able to write the rate law from in order to generate the rate law from the hypothesis that needs, by definition, to match this rate law that was determined experimentally. Now, how do we do that? All right, so what we're going to do now is we're going to basically estimate, if you will, the rate law based on what we call the molecularity of the reaction between the NO2s in the elementary step. So what is molecularity? All right, so what I've done here is defined it for you. The molecularity is a complicated term that basically what it means is that we're going to estimate the order of reaction of the elementary step based on the number of collisions between molecules. And what I've done here is laid out the basic definitions for the viewer so that you can see them. So if we focus first on this top equation, if we had a single entity, a single molecule that I'm going to call A here, shown here, this would be unimolecular because whatever's going to happen to A is based solely on one molecule of this particular substance. So we would say for this that X is going to be 1, just the same as we would have done it experimentally, but now what we're going to do is literally propose the order of the reaction based on the number of collisions that we see occurring within the elementary step as it's written. So if we focus on the next step down here, you see that there's 2 molecules of A that have to collide in order to react. So we would say this step is bimolecular, and we would establish the order of reaction for this particular kind of elementary step as being X is equal to 2 rather than X equal to 1, where the case is that you only have 1 molecule present. Where we have two substances that are colliding, that are different, just like with the experimental rate laws, where these two substances would be first order in each of them. So we would say for the A that this is going to be first order in the A, we're going to have first order in the B, but overall this would still be bimolecular because you need a collision between A and B in order for the reaction to happen. So overall this is going to still be a second order reaction with respect to the fact that both A and B have to collide. And then lastly, in the situation where we have 3 molecules of some kind of substance that have to collide, we would call this step a trimolecular event. But it's extremely rare because if you think about this for a minute, in order to have a chemical reaction that involves the simultaneous collision between 3 things is going to be statistically not an event that's going to happen very often. You would expect this kind of reaction to be really, really slow. All right. Now with that, let's go back to the example. All right. So now what we're going to do is evaluate my step number 1 here, and here's the thing. to predict the reaction order from a series of elementary steps, it's got to be based on the rate limiting step, because the rate limiting step determines basically how fast the reaction is going to go. So the order of reaction has to be determined from the rate determining step. Only now what we're going to do is we're going to predict it based on the molecularity, literally, of the reactants. And in this case, you can see that we have the collision of two NO2 molecules. So for this, we would write a proposed rate law, again, a hypothesis that would look like this. Here's my rate constant, and then we're going to have my NO2 concentration, and it's bimolecular because we have the collision between literally two of these molecules. And you can see when you inspect this that this rate law is equivalent to the rate law that was determined experimentally. These two things are the same, and therefore this set of elementary steps we would say is possible, and I emphasize the word possible. This doesn't mean that this set of elementary steps absolutely happens. The chemist would have to go back into this now and develop some experiments that would allow them to discern whether or not their proposal was actually happening. All right. And with that, I'm going to go ahead and close the video. I would like to thank the viewer for taking the time to watch my presentation. Please come back and also check out my website at www.chemdoctor.org.